Hi, I'm George Karlos and I'm a first year PhD student at Vrije Amsterdam. I will present our vision for unified programming for in-network computing. Recent advances in networking hardware have allowed switches to become programmable while keeping performance similar to fixed function switches. This has allowed to accelerate network functions by running them on the data plane. Programmable switches have also been used for application-specific computations like caching, machine learning, and data transformations. In this work, we focus on this kind of application-specific computations that we collectively refer to as in-network computing. Programmable switches are packet processing pipeline architectures. Packet headers are extracted by a parser and go through a processing pipeline. At each stage, match action tables match on header fields with actions that can modify the headers. In the end, a deep parser reconstructs the packet. A switch program describes the state machine of the parser, the match action tables and their conditional application, and the serialization of headers in the deparser. This programming method works very well for networking, but it is not as great for expressing compute. There are three main issues with using data plane programming languages like P4 to express compute. First, the semantics are rather complex and unfamiliar. To give you an example, a cache lookup is pretty straightforward. Check if the key is in the cache, check its validity, and read the value. However, in P4, we have to translate this into table application logic. We must apply a table to look up the key and define actions that write the outcome as metadata, and then repeat to check if the value is stale, and then apply a few more tables to read the value from memory. Second, INC applications are encoded as custom protocols. This means we have custom packet formats that the host must craft and the switches must recognize. The underlying networking protocols must also be incorporated, which requires good networking knowledge from the programmer. Finally, a disjoint development process leads to subtle incompatibility bugs, which increases development and maintenance costs and complicates deployment. So, in short, if we want to compute on switches, we need something better. Our proposal is to treat switches as accelerators and express compute as kernel functions they can execute, and program them as part of the application. To do this, we need to answer the following questions. What kind of data should kernels operate on that is at a higher level than packets, and what kind of interfaces to expose to the programmers? Also, how to compile kernels down to switch programs, and how can INC applications written this way fit the target platform, which is a network of hosts and switches? To that end, we first proposed the C3 model for INC programming. C3 has two components. The first is data windows. These are the basic unit of processing in C3. They are constructed by associating elements from host arrays, and how they map to packets depends on the implementation. The second is network kernels. These are point-to-point communication primitives for Windows that also compute on them. Outgoing kernels are invoked by a host to send data one window at a time and compute on it on the switches along the way. They can also make forwarding decisions for Windows. Incoming kernels are invoked by hosts to receive Windows. But let's better look at an example. Here we have two hosts connected to a programmable switch. Host A has some local arrays, and now it invokes an outgoing kernel to send them to B. The first thing that happens is that windows are formed. In this case, the programmer associated two elements from each array, so windows of 4 elements in total are sent out one by one. When a window reaches the switch, the kernel executes. It uses window data and switch memory to do its computations, and in this case, ends up modifying the window. The outcome of the kernel, in this case, is to forward the window to B. B must invoke an incoming kernel to receive that window and process it further. In this example, windows were constructed by vertical splits of uniform length. However, window construction is programmer defined and more combinations are of course possible. So what we want to build is a complete programming system that implements C3. At the top, we have the net compute language. NCL is a C++ extension for defining kernels and switch resources. The abstract network description is an overlay network configuration of the functional components of the application. When a kernel makes a forwarding decision, it must be to a valid label from that file. The runtime uses the net compute protocol to transport Windows and kernel execution context. This mechanism is completely transparent to the programmer. Finally, we have an LLVM-based compiler that generates programs for both hosts and switches. Application deployment is strictly speaking not part of the system, but we do want to build an external mechanism that maps the abstract network description to the actual network and ensures connectivity by populating routing tables. So now let's look at an example NCL program. We're going to build an in-network AllReduce operation. A number of workers are connected to a programmable switch and each one holds an array. and the goal is to sum up the values at each position across the arrays and serve the result. This is the code for the NCL implementation, but let's break it down and see what happens. First, we declare some switch memory. The first one is the accumulator array, where we make implicit aggregation slots that have the size of a window. The count array tracks how many windows have been aggregated per slot, and when it reaches n, we broadcast the result. And finally, we have a control variable for the number of workers that participate. A control variable is written only by host code. This is the outgoing kernel with the switch logic. The first thing to notice is this window struct. It is a built-in struct that carries metadata for the current window and is extendable by the programmer. The kernel uses it to compute a global index for the first element of this window and then loops over the values in the window and accumulates them. Then it increments the counter for this slot and checks if the slot is done. If done, it copies the result back to the window and resets the slot. And finally, it broadcasts the window. If the slot is not done, then the window is dropped. This incoming kernel is used by hosts to receive the results. Its parameter list extends that of the outgoing kernel so that, for instance, we can pass a pointer to copy the results to host memory. The host code first sets the number of workers, and then it invokes the outgoing kernel on the data array, and with a specification for how to construct windows. Then it goes in the loop, invoking the incoming kernel at every iteration. The done flag is also passed as an extra argument so that the loop breaks when the last window is received. Even though we have simplified the code a bit, the important thing is that at no point we had to define a protocol or deal with packets. We can also use NCL to build an in-network cache, so if you're interested, you can find that example in the paper. The NCL compiler is based on LLVM. The frontend is mostly Clang itself with some source level checks and rewriting. Building on Clang allows us to easily generate LLVM IR from NCL source code. The frontend outputs one IR module for host code and one for switch code. Then we have a dual middle and backend pipeline. The host pipeline is mostly Clang's LLVM passes for the host target architecture. The switch pipeline lowers LLVM IR to P4. There are 4 stages in the switch pipeline. At the conformance stage, we do IR level checks to discard programs early if they for sure cannot be compiled. Our ultimate goal is to define a subset of the LLVM IR for which we can make some sort of compilability guarantees. NCL allows to place kernels in switch memory to specific switches. In the versioning stage, the IR is split into multiple modules based on switch location. If there are location conflicts, the program is rejected. In the next stage, we do analysis and transformations to map the IR to P4 target. First, we unroll loops, inline function calls, and do common early stage SSA transformations. Next, we map the control flow graph to a table graph for an idealized match action pipeline of arbitrary length. The compiler can also make high-level decisions, like for instance move part of the control flow graph to the parser. Finally, the IR is mapped to a specific P4 target, so the control flow graph is placed to the programmable blocks the target defines. In the final stage, we translate the module to P4. The outcome is modular P4 blocks that we can merge with a template program with the networking behavior of the switch. For this step, we want to build on prior work on P4 to LLVM compilation and P4 program composition. The outcome is a switch program where the compute module executes if the packet contains NCP headers, otherwise the switch proceeds with its normal networking behavior. The output can then be given to a P4 compiler or backend. Our goal is to either gather compiler feedback and try again, or encode chip restrictions into the NCL compiler. However, it is unclear how to first obtain this information for the current chips, or what guarantees can be made even with this information. To summarize, we have identified the issues with using current data plane programming methods to express compute, and as a solution, we propose the net compute language that unifies switch and host programming. It is based on our proposed C3 model that treats switches as accelerators for computational kernels. The data window abstraction hides packet processing concerns, and window communication is handled transparently by the NCL's runtime. An abstract network description defines the application view of the network and can be used for deployment. Finally, we propose a compiler that generates P4 and merges it with a template P4 program with the switch's existing networking behavior. As we're in an early stage, we're open to suggestions or collaborations, so feel free to contact us with any remarks or questions about our work. We also encourage you to check our paper for more details. Thank you.